Alright, in this section 10.4 we work some more with revenue, profit, costs, typically maximizing things, but every so often we minimize things as well. In example 1, they give you an equation here, and n represents n of t. The function finds the number of employees based on t, which is the year, a number of years after 2017. So they want you to maximize n, meaning find in what year there will be a maximum number of employees. So you're taking this function and taking the derivative. So if you take that function and you multiply by 8 times each part in here, you get this, and then when you get a common denominator, you get this, and then you combine like terms. So this is about as simplified as you can get before you take the derivative. So we're going to use the quotient rule, bottom derivative of the top minus top derivative of the bottom over the bottom squared. And when you multiply everything out, 4 of the terms go away, and you get this guy here. Now when you set that equal to 0, your denominator doesn't give you any real answers, because t squared plus 16 is never equal to 0. But your numerator is going to give you an answer. So when you set the numerator equal to 0, you can factor out a 1280, and then what's left factors to 4 plus t, 4 minus t. Setting each of those equal to 0 gives you t equals plus or minus 4. And since t is the number of years after 2017, a negative 4 does not make any sense, so we throw that one out. And so we're strictly looking at greater than 0 and less than 10, so we use a sign diagram with dividing it up using the critical value we found of 4. I plug 1 into the derivative and I get a positive number. I plug 5 into the derivative, I get a negative number, so we get plus minus here. So that tells us that this is a maximum, and that's what we're looking for. 4 years after 2017 is when you get a maximum number of employees, and when you plug 4 into the original function, you get 168 employees. 4 years after 2017 is the year 2021, and if you look at this graph, you can see that at 4 you do get a maximum there. This one talks about maximizing a quantity, but you need to write things in terms of just one variable. So a farmer is enclosing a pasture, and he has to put a fence along the road, and that fence is more expensive, so it costs $15 a foot. And these other two fences are only $10 a foot, and he doesn't need to put a fence along the river because the river is a good boundary. And with these different costs per foot, he wants to calculate how to minimize his cost for the fence, and he wants the fence to be containing in 1.6 million square feet. Alright, so if you're talking about two different formulas here, one is cost, one is area. The area is length times width, so it's x times y, and it's 1.6 million. So when you solve this for y, you get y equals 1.6 million over x. Now over here, your cost is the length times the cost per foot. So 10x, 10y, 15x. And so you got all three of those that add up to your total cost, and these two give you 25x. And now if you replace y with what we know y equals, now you've got this whole thing in terms of just x. And you can write that as 16 million over x, or 16 million x to the negative 1. That's easier to take the derivative that way. So when you take the derivative, you get 25, you get minus 16 million x to the minus 2. You cross the fraction bar with that, get a common denominator and bring it together. So now when you set the denominator to 0, that doesn't give you any answers. But the numerator, when you set that equal to 0 and factor out a 25 and then factor what's left, you end up getting plus or minus 800. But again, this is a length, so you can't get negative 800 feet, so you cross that off. And we're looking at this one here when we divide up the number line with make a sign diagram for greater than 0. And so we find that based on plugging numbers into the first derivative, we get a minimum here at 800. That's what we're looking for. We're trying to minimize. And so X is 800, so you plug 800 in for X and you get Y is 2000. And then if you plug 800 into the cost function, you get 40,000. So our dimensions are 800 by 2,000, and our costs are $40,000. And if you look at this here, this one shows that here you got X is 800, that's a minimum there. And I think the 40 for the Y is your cost in thousands. Number 3, postal restrictions. When you send something by post, they have a thing which they call the length plus the girth must not exceed 108 inches. Now the girth is simply all the way around the object, and then the length is obviously the other dimension. And when you add up these 4 sides along with this length as well, that cannot go any greater than 108. So we know we got side, side, and length, and we know the volume is side times length, or side squared length. We also know S plus S plus S plus S plus L is 4S plus L, and that equals 108. So L is 108 minus 4S. So in place of L, you put 108 minus 4S, and now you multiply that out, and now you got volume in terms of only S. So now you take the derivative and factor, and set each factor equal to 0. This one gives you side equals 0. That makes no sense. The side has to have a positive distance. This one will give you 18, and you check 18 with your sign diagram, and you get plus minus, so it's a maximum there at 18, and that's what we're trying to do, is maximize the volume. So when you plug 18 into the volume here, you get 11,664 inches. So when S is 18, go up here and plug 18 in there, and you get L is 36. And here's your graph that shows that when S is 18, you get a maximum in volume. Next, we're going to consider inventory cost models, in which a certain number of items are produced in each production run, and items are removed from inventory at a fixed constant rate. So they're being sent out to the store, or they're being sold off the shelf. Either way, the inventory is continually decreasing, and each time you've got to re-up or reload those shelves with new inventory. So each time you're making another production run to create more of the model that you're selling here. And because items are being removed at a constant rate, we can say the average units in storage is 1/2 X. If X is here and 0 is there, roughly between here to here, it's 1/2 X, so X over 2. And this is the time between each run. Alright, so in these models, costs are associated with both production and storage, but lowering one of the costs means increasing the other. To see how inventory cost models work, consider the following example. Suppose a company needs 1 million items during a year, and that preparation costs are $800 for each production run. Suppose further that it costs the company $6 to produce each item and $1 to store it for up to a year. If each production run consists of X items, find X so that the total cost of productions and storage are minimized. Alright, so what are your production costs? Well, you've got a certain number of runs, and for each run there's a cost to it. So the cost per run times the number of runs, that gives you a dollar amount, plus the number of items you're making times the cost per item you're making. Now the number of runs is 1 million divided by X, where X is the number of items you make in each run. So if you take 1 million and divide it by, let's say, 100,000, that means you're making 10 runs. So X is how many items you make in each run. Divide that into 1 million, and that will tell you how many runs you're going to be doing within the year. Maybe one every month or one every 6 months, who knows. And the cost for each run is 800. So 800 times the number of runs. Now the number of items, we know that to be 1 million, and we know the cost for each item is $6. So you multiply these guys together and you get this. Now what about storage? So the average number of items stored, we know that's x over 2. And the storage cost per item is $1. So x over 2 times 1 is just x over 2. So now what's your total cost? You're taking this guy and adding them together. So this is your first guy, this is your second guy, and you're adding them together. And now I'm rewriting it so it's easier to take the derivative. And so now when I take the derivative, I get this guy, which I can rewrite as one. Normally I combine this to make it one big fraction, but this time I didn't do that. I just moved this guy over to the other side, making it positive. Then I cross multiply and I get x squared equals 1.6 billion. I take the square root and I get x equals either 40,000 or negative 40,000. X is the number of items in each production run, so you can't get a negative number of items, so throw that out. If you take the second derivative, you get this guy, and if you plug the critical value into that, you get a positive, which means that this is a absolute min. So 40,000 is the absolute minimum, and that will reduce your costs. And it's the number of items in each production run. Sometimes problems that we studied cannot be done any other way except with a graphing calculator or Excel. Our first goal is to express the quantity to be maximized or minimized as one variable. Then when we graph it, we can use the graphing calculator to give us an approximation of a pretty good guess as to what our answer should be. Alright, a developer at a campground here must pay for a utility line installation to the community center from the transformer. So he's running a line from this transformer to this community center. Alright, because of restrictions, the lines must be underground on the property. Over here, when you're not on the property, you don't have to dig it underground, but over here you do. Suppose the costs are $50 per meter along the street, and $100 per meter for underground, because you have to dig underground. It takes more work and labor involved. So how far from the transformer should the line enter the property to minimize installation costs? So they're asking this distance right here, this 100 minus x. Well, if you figure out what x is, you can just do 100 minus x and you got it. Notice that this entire length is 100 meters. This is 48. And we don't know what this is, so we're just calling it x, and then whatever this is has to be 100 minus x. It has to be. So now let's say you do go straight across and then straight down. That's going to be 48 meters times $100 for each meter. That's going to be 100 meters at $50 per meter, and that's $9,800. All right. Most likely we can get that number reduced. Let's see how we can do it. So if we create this triangle here with 48 and x, we know that this guy, L, we know by Pythagoras, we know x squared plus 48 squared equals L squared. That's Pythagoras. And if we solve that for L, we take the square root of both sides and we get this guy equals L. Alright, so if that's L, and that's underground, we're multiplying by 100. And then the 100 minus x, we're multiplying by 50 because it's not underground. And so this is our cost function. So we know it's limited between 0 and 100. And so now we graph this guy, and what we see is that it does have a minimum. And how do you find that point? Well, you type this into your calculator under y1, and then you adjust your window properly. You probably want to adjust your window between minus 25 to positive 125, so you can clearly see what's happening between 0 and 100. And now how do you get these values here? Very easily. Just hit zoom 0. When you hit zoom 0, it will adjust the y values so that you can see the graph. If you get the x values properly by hitting window and typing in x min, minus 25, x max, 125, don't worry about x scale. Just type just change your Xmin and Xmax properly, and then once you hit graph, after you've graphed it, then hit zoom 0, and you'll see a nice graph just like this one. Alright, so once you see this window here, just hit second trace 3, and that will help you to find a minimum. You'll move to the left of the point, hit enter, move to the right of the point, hit enter, and then move towards the point where you think it roughly is, and hit enter. And it will give you these numbers right here, which means X is 27.7 meters. The cost is a little over $9,000, cheaper than the 9,800 that we initially calculated. But we're actually not looking for X, we're looking for 100 minus X, which is the difference, which is 72.3 meters. Alright, so let's look at the questions that you're going to see on WebAssign, or similar to the questions you'll see on WebAssign. There's not that many. I think there's like 8 or 9. Alright, the profit per acre of a grove of orange trees is given by this expression, where X is the number of orange trees per acre. How many trees per acre will maximize the profit? So your profits in terms of X, so P of X equals this, which is this guy here. Take the derivative, set it equal to 0, and solve, and you get 100. So that means, well, I took the second derivative as well, and I got a negative number, which means the second derivative is always negative, which means if we find a critical value, it is a maximum. And so 100 acres per tree will maximize your profits. Number 5, the daily output of a factory during an 8-hour shift based on T number of units Y produced after T hours of production. So T is your number of hours that you've been in production, and it ranges from 0 to 8. So after how many hours will the hourly number of units be maximized? So you take the derivative of this guy, and you get this. Set it equal to 0, factor. Set each factor equal to 0, and you get a negative time, doesn't make sense. Positive time, this is possibly a good answer. Take the second derivative and plug 5 into it, and it's negative, so that lets you know that it is a maximum. Now what is that output? Well, you plug the number you found into the original function, and you get 237.5. Number 8, suppose the monthly cost in dollars of mining a certain ore is related to the number of pieces of equipment used. And so they give you C here, where X is the number of pieces of equipment and C is the cost. So we want to minimize the cost. So we're taking the derivative of this guy. I rewrote it this way so it's easier to take the derivative. I got a common denominator, brought it together, and I set the denominator equal to 0 and numerator equal to 0 and solved each one. This one doesn't really give you a real answer. This one does. It gives you plus or minus the square root of 34.8. But you can't get a negative number of pieces, so that's out. And this one is 5.899 approximately. And so if you use your sign diagram with greater than 0 and 5.889, or 899 actually, with your as your critical value, if you check the first derivative with 1 and with 6, then you find minus plus, and that tells you that is a minimum. So if you want to minimize your cost, you want to use about 6 pieces of equipment. 11 talks about advertising. It says an inferior product with a large advertising budget sells well when it's first introduced, but the sales fall as people discontinue use of the product because it's inferior. S is your weekly sales, and T is the number of weeks since the advertising started. So we want to maximize sales, so we want to know in what week will the sales be maximum. So you're taking the derivative of this guy, and you got to use the quotient rule. Now, a helpful hint here, I guess you don't necessarily need to do that because it's not that complicated. But I factored out a 200 and a t plus 1, 200 and a t plus 1. And when you take a 200 and a t plus 1 out of this, you're left with a t plus 1. 200 t plus 1, you're left with t, and 200 and 200 and t plus 1, you're left with a 2t there. So this part just gives you 1 minus t, and here this part cancels with the t plus 1 in the denominator. So it leaves you with the denominator cubed, and the top is a lot simpler than if you didn't cancel that t plus 1. So set the numerator equal to 0 and solve, and you get t equals 1. Set the denominator equal to 0 and you get t equals negative 1, which doesn't make sense. Time is not negative. So now when you check the one critical value of 1, you find plus minus, and you get a maximum, which means these sales will reach a maximum after week number 1. Alright, 13. Suppose that the percentage P of people who could correctly identify 2 of 8 defendants in a drug case T days after the trial began is given by this. Find the number of days before the percentage is maximized. And you want the percentage of people who can correctly identify, you want that to be a maximum so that you get as many people identified as you can during the trial. So you take the derivative of this, and when you take the derivative of that constant, that part just goes away, but this part is a quotient. It gives you this guy here. You set it equal to 0. Bottom gives you nothing, but the top gives you plus or minus 8, and you throw out the 8. And when you check positive 8, you get a plus minus, which tells you it's a maximum 8 days after the trial begins. So 8 days after the trial begins is when the highest percentage of the people can identify defendants in the drug case. And how many can they identify, or what percentage can they identify? You plug 8 into the problem and you get 0.45 or 45% of the people. Alright, 15 says you got 2 equal rectangular lots. They're enclosed by fencing and the perimeter. Closed by fencing the perimeter, and you've got a fence down the middle. Each lot contains 1,200 square feet, and they want to minimize the fencing. So we know that each lot is x times y, and that's your area of that. Each one is x times y, and each one is 1,200. So when you solve that for y, you get 1,200 over x. Now what's your perimeter, or meaning your total length of fence? It's 3 x's and 4 y's, so 3x plus 4y is your perimeter. And in place of y, we can put in what y equals 1,200 over x. And so now you've got this guy here, and when you take the derivative and write it as one fraction, now you're ready to set it equal to 0. And the denominator gives you nothing, but the numerator gives you plus or minus 40. That's a length, so you throw out the negative. And so with positive 40, you're talking about a minimization. And so we know that x equals 40. When you go back and plug 40 into that, you know y equals 30. And so now when you plug 40 into the perimeter function, plug it into this one, I guess, you will get 240 feet of fencing. All right, 17. 17, you've got a rectangular field with one side along a river, and the one side here, its fencing is $40 per foot, and these other two sides is only $10 per foot. And they want to minimize the cost, but they want it to contain 45,000 square feet. So you got area is x times y equals 45,000, so y equals 45,000 over x. What is your cost? It's x plus y, but each one is not only the length, but times the cost per foot. So 10x, 10x, and 40y. And that's 20x plus 40y, but y can be replaced with what y equals. And so now you've got this guy here. When you take the derivative, get a common denominator together and set it equal to 0. You get x equals 0, which makes no sense, but when you set this equal to 0, you get 300 or minus 300, and you can't have a negative length, so you throw out the minus 300. And so when you check positive 300, you get a minus plus going on there, so that means it's a minimum, and that's what you want. So if x is 300, 45,000 divided by 300 is 150, and so there's your dimensions that will minimize your cost. This one's pretty hard. It's not that easy to do this one. So you got a rectangular box, and they say the length is twice as much as the width, and the volume's 256. Now the material for the top costs 50 cents per square inch, and all the other 5 sides cost 25 cents per square inch. Find the dimensions that will minimize your cost. So first we got to write each of these different dimensions in terms of only one variable. So first we started with volume equals length times width times height. We know that. And also we know that the length or the length is twice as much as the width. So it takes 2 widths to equal 1 length. Now be careful there, because when they typically say the length is twice as much as the width, a lot of people want to say 2L equals W. But no, the length is twice as much as the width, so you need 2 of the widths to equal just 1 of the length, because the length is really long, and you need 2 of those widths to equal the length. All right. So when you solve this for W, you get W equals L over 2. And if you say the volume equals 256, and you let W equal L over 2 like we found, you get this here. When you multiply both sides by 2, and then divide by L squared, now you know H in terms of L. So you got W in terms of L, H in terms of L, and L is of course in terms of L. So L is L, W is L over 2, and H is 512 over L squared. Alright, so now let's look at the different sides here. You got the top, and the top has dimensions of W and L just like the bottom does. Top and the bottom are the same dimensions. So the area of the top is W times L. The area of the bottom is W times L. The area of the side, this side here is W times H, and there's 2 of them, so 2 times HW. And then the front and the back are H times L, and the front is H times L, and there's 2 of those, so 2HL. And now what I did was I replaced the W and the H with what each of the W and the H are equal to, and that gave me these guys here. Now this first one is 50 cents per square inch, so you multiply it times 0.50. These other 3 are 25 cents per square inch, and you add them together and multiply by 0.25. So when you multiply all these guys together and combine like terms, you get this guy here. So that's your cost function in terms of only one variable, L. Now when you take the derivative, you get this guy here, and you get a common denominator, bring it together, and you set the denominator equal to 0, which doesn't give you anything, and you set the numerator equal to 0, which gives you L is 8. All right? So once you know L is 8, you go back here, and if L is 8, W is 8 over 2, which is 4, and H is 512 over 8 squared, which is 8. So you got the 3 different dimensions, and you can plug 8 into the cost function. When you plug 8 into this cost function here, you get a cost of $72 for the construction of the bot.